Today's class, I'm going to explain electrochemical machining. Aim of this session to familiarize students with electrochemical machining. Instructional objectives. This session is designed to understand the working principle of electrochemical machining, identify process performance variables, and learning outcomes. At the end of the session, you should be able to understand the process characteristics, know advantages and disadvantages and the applications of electrochemical machining. Electrochemical machining is a non-traditional machining process that uses the principles of electrochemistry to remove material from a workpiece. It is primarily used for precision machining of complex shapes and intricate profiles that are difficult to produce with conventional machining methods. In ECM, a tool called the cathode and the workpiece, which acts as an anode, are immersed in electrolyte solution. During the ECM process, material removal occurs through the combined action of electrolysis and mass transport. The electrolyte provides a conductive path for the current flow and carries away the dissolved material from the workpiece. The shape and size of the mechanical feature are controlled by the shape of the cathode and the current density distribution. Electrochemical machining is a specialized process that offers unique capabilities for precision machining of complex parts, making it a valuable technique in certain manufacturing applications. Now let us see that the setup of electrochemical machining. So that is electrolyte, and there is a pipes and pump which is pump the electrolyte via filters and the pressure gauges and flow meters, and keeping the workpiece under the fixture in an enclosed chamber, and the tool is connected, tool and workpiece connected to the DC power supply. Okay. The key main components of an AC system, that is a power supply. It provides the necessary electric current for the electrochemical reaction to occur. The current is usually using the direct current, that is DC current. The second is electrolyte. It is a conductive solution that facilitates the transport of ions and a dissolution of material from the workpiece surface. The choice of electrolyte depends on the material being machined and the desired machining parameters. Next is a cathode. The tool or electrode that is connected to the negative terminal of the power supply. It is usually made of a conductive material like copper or graphite and is shaped to match the desired shape of the machined feature. What is the shape of the feature, the machined feature? The same shape we are providing the tool also. The next is anode. The workpiece that is connected to the positive terminal of the power supply, it is typically made of a conductive material like stainless steel, titanium or other metals. It acts as an anode. So the working principle of electrochemical machining involves the controlled removal of material from a workpiece through electrochemical reactions. Here is a step-by-step explanation of the process. Now first we will see the setup. The ECM setup consists of a power supply, electrolyte solution, cathode act as a tool, and anode act as a workpiece. And the workpiece is connected to the positive terminal of the power supply, while the cathode is connected to the negative terminal. Both the cathode and anode are immersed in the electrolyte. Next, electrolyte flow. The electrolyte solution is circulated between the cathode and anode. This ensures that fresh electrolyte continuously reaches the machining zone, carrying away the dissolved material and maintaining a stable electrolyte environment. Next, electric current application. The power supply is switched on and a DC voltage is applied between the cathode and the anode. This establishes an electric circuit allowing current to flow through the electrolyte and the workpiece. Electrochemical reaction. As the current flows, electrochemical reactions take place at the surface of the workpiece. The electrolyte provides a conductive path for the ions to move between the cathode and the anode. The workpiece material undergoes anodic dissolution where metal ions are released into the electrolyte. Material removal. The metal ions that are released during the electrochemical reaction are carried away by the flowing electrolyte. The dissolved material is gradually removed from the workpiece, resulting in the desired shape and profile. The material removal rate depends on various factors such as current density, electrolyte composition, and the workpiece conductivity. Shape control. The shape and size of the machined feature are determined by the shape of the cathode and the distribution of current density. The cathode is designed to match the desired shape of the machined feature, and the current density can be controlled by adjusting the parameters of the power supply and the electrolyte flow. So next, what are the performance of electrochemical machining? Electrochemical machining offers several performance advantages and the considerations. First is the precision. The ECM is known for its exceptional precision and accuracy in machining complex shapes and intricate details. It can achieve high surface finishes and dimensional tolerances, often in the range of micrometers. The process is capable of producing intricate features that are challenging to achieve with conventional machining methods. Second one is material compatibility. ECM can effectively machine a wide range of electrically conductive materials, including metals and alloys. It is particularly useful for materials that are difficult to machine using traditional methods such as heat-resistant alloys, hardened steels, titanium, and super alloys. ECM does not depend on the material's hardness or brittleness, making it versatile in handling various workpiece materials. No thermal damage. Since ECM is a non-thermal process, there is no heat flow, heat affected zone, or thermal damage to the workpiece. This is particularly beneficial for the materials that are sensitive to heat, prone to distortion, or have surface coatings that could be affected by high temperatures. ECM avoids the issues of thermal stresses, microstructural changes, and residual stresses associated with conventional machining methods. Next, complex geometries. ECM is well suited for machining intricate and complex geometries. It can produce features with internal cavities, thin walls, sharp corners, and fine details that are challenging to achieve using conventional machining. The process allows for high design flexibility and ability to create customized components with intricate shapes and contours. Limited tool wear. In ECM, the cathode experiences minimum wear since the material removal occurs through the electrochemical reaction rather than mechanical cutting. So this leads to extended tool life and reduced tooling cost compared to traditional machining processes. However, it's important to monitor and maintain the condition of the cathode to ensure consistent performance. Burr-free and smooth surfaces. ECM typically produces burr-free surfaces, reducing the need for secondary deburring operation. The electrolyte continuously flushes away the dissolved material, resulting in smooth surface finishes. This advantage is particularly valuable in applications where surface quality and elimination of the post-processing are critical. Next, process efficiency. The ECM can be a relatively slow machining process compared to conventional methods. However, it can be highly efficient for applications where precision and complexity are paramount. The overall efficiency depends on factors such as current density, electrolyte composition, and workpiece conductivity, which can be optimized for specific requirements. What are the demerits of electrochemical machining? The electrochemical machining also having the demerits. So limited material compatibility. ECM is primarily suitable for electrically conductive materials. It cannot be used for non-conductive materials such as ceramics, plastics, and composites. This limitation restricts its application range as certain industries and components may require machining of non-conductive materials. Slower machining speed. ECM is generally a slower machining process compared to conventional methods like milling or turning or drilling operations. The material removal rate in ECM is relatively lower, which can lead to longer cycle times for machining operations. This can be disadvantageous when high productivity or fast turnaround times are crucial. In cases, it may not be supplied. Next, complex process control. ECM requires precise control of various process parameters, including the current density, electrolyte flow rate, temperature, and composition. Achieving and maintaining optimal process conditions can be challenging, and slight deviations in these parameters can impact the machining results. Strict process monitoring and control are essential to ensure consistent and desired machining outcomes. Next, environmental considerations. The electrolyte used in ECM can contain chemicals that may pose environmental and disposal challenges. Some electrolytes may be toxic or hazardous, requiring proper handling, storage, and waste management practices. Compliance with environmental regulations and safety precautions is necessary to mitigate and potential risk. Equipment and setup cost. The initial investment for ECM equipment can be relatively higher compared to traditional machining tools. The need for specialized power supplies, electrolyte management systems, and custom designed cathodes adds to the setup cost. This can be different for smaller businesses or applications that have budget constraints. Limited stock removal. ECM is more suitable for precision machining and fine finishing operations rather than heavy stock removal. The process is not as efficient when significant material removal is required. Therefore, for applications where extensive material removal is needed, ECM may not be the most efficient choice. Skill requirements. ECM is a specialized machining techniques that demands skilled operators with a deep understanding of the process principles and the ability to troubleshoot potential issues. Training and expertise are necessary to achieve optimal results, maintain process control, and address any unexpected challenges that may arise during machining operation. I hope everyone understand the electrochemical machining and setup, what are the process parameters, what are the merits and demerits. Thank you.